Picture this. You're stranded in the middle of the Sahara Desert, dying of thirst, with nothing but sand stretching endlessly in every direction. But what if I told you that even in this bone-dry wasteland, there's actually water floating all around you right now, invisible to the naked eye, just waiting to be harvested? That's not science fiction anymore. 3 brilliant scientists just won the Nobel Prize for creating materials that can literally pull drinking water out of thin air. And this breakthrough could change everything we know about water scarcity forever. I'm talking about technology so revolutionary that it sounds like magic. Materials that can suck moisture from the atmosphere even in the driest places on Earth, turning humidity into clean, drinkable water without needing any external power source. And the best part? This isn't some distant future fantasy. These water harvesting materials are real. They're working right now, and they could solve one of humanity's greatest challenges. But here's what's really mind-blowing about this discovery. The inspiration didn't come from some high-tech laboratory or Silicon Valley startup. It came from studying desert beetles, cacti, and spiderwebs. Nature has been pulling water from air for millions of years, and these Nobel Prize winners just figured out how to copy those tricks and make them even better. Let me break down exactly how this incredible technology works, because once you understand it, you'll realize we're looking at one of the most important scientific breakthroughs of our lifetime. The science behind atmospheric water harvesting relies on a surprisingly simple principle that's been hiding in plain sight. Air always contains water vapor, even in the driest climates you can imagine. The trick isn't finding the water, it's capturing it and turning it into something you can actually drink. The winning materials work through a process called adsorption, which is completely different from absorption. Think of it like this. Absorption is when a sponge soaks up water, but adsorption is when water molecules stick to a surface like magnets. These revolutionary materials have surfaces so precisely engineered that water molecules from the air are irresistibly attracted to them, even when there's barely any humidity present. What makes these materials so special is their incredible surface area. We're talking about structures with internal surfaces so vast that a single gram of material can have the same surface area as an entire football field. Imagine trying to dry your clothes on a clothesline versus spreading them across an entire stadium. The more surface area you have, the more water you can capture from the surrounding air. But surface area alone isn't enough. The real genius lies in how these materials control the interaction between water molecules and their surfaces. The Nobel Prize winners discovered how to fine-tune the material's properties so that water molecules stick when you want them to stick, and release when you want them to release. It's like having a molecular-level switch that you can flip on command. The process happens in cycles that are almost poetic in their simplicity. During cool nighttime hours, when humidity is naturally higher, the material acts like a super-efficient sponge, collecting water molecules from the air and holding onto them. Then, when the sun rises and temperatures increase, the material releases all that captured water, which condenses into liquid form and can be collected for drinking. Here's where it gets even more fascinating. Different research teams have developed various approaches to this water harvesting challenge, and each one reads like something from a science fiction novel. Some materials use metal organic frameworks, which are like molecular cages that trap water molecules inside their intricate structures. Others use specialized polymers that change their properties based on temperature and humidity levels. One particularly clever design mimics the way desert beetles survive in the Namib Desert, one of the driest places on Earth. These beetles have bumpy shells with hydrophilic spots that attract water and hydrophobic areas that repel it. Water collects on the attractive spots and then rolls down the repelling areas, eventually dripping into the beetle's mouth. Scientists created artificial surfaces that copy this exact mechanism, but make it thousands of times more efficient. The numbers behind this technology are absolutely staggering. In laboratory tests, some of these materials can produce several liters of clean drinking water per day from just 1 kilogram of material, even in desert conditions with humidity levels as low as 10%. To put that in perspective, that's like creating a full day's worth of drinking water for multiple people using nothing but a device the size of a thick textbook. But let's talk about why this matters so much for our world right now. Water scarcity affects over 2 billion people globally, and that number is growing every single year. Climate change is making droughts more severe and more frequent. Traditional water sources are becoming unreliable or completely disappearing in many regions. Meanwhile, population growth means we need more water than ever before. Current solutions to water scarcity are expensive, energy-intensive, and often impractical for remote areas. Desalination plants require massive amounts of electricity and only work near oceans. Transporting water over long distances is costly and logistically challenging. Drilling wells isn't always possible, and groundwater supplies are being depleted faster than they can be replenished. That's what makes atmospheric water harvesting so revolutionary. The atmosphere contains roughly 6 times more water than all the world's rivers combined. It's a renewable resource that's available literally everywhere on the planet, even in the middle of deserts. And unlike other water sources, atmospheric water doesn't compete with existing ecosystems or agricultural needs. The potential applications are mind-boggling. Imagine refugee camps that can generate their own water supply without depending on aid deliveries. Rural communities in developing countries could have access to clean water without expensive infrastructure projects. Military units could operate in remote locations without worrying about water logistics. Even space missions could use this technology to create water on Mars or the Moon. But perhaps most exciting is how this technology could transform agriculture. Farmers in arid regions could use atmospheric water harvesting to irrigate crops without depleting local water supplies. Vertical farms and greenhouse operations could become completely water independent. We could grow food in places previously considered too dry for agriculture. The manufacturing potential is equally impressive. Industries that require large amounts of clean water could set up operations anywhere, not just near existing water sources. Data centers, which use enormous amounts of water for cooling, could become completely self-sufficient. Chemical plants could operate in remote locations where valuable raw materials are found. However, like any revolutionary technology, atmospheric water harvesting faces real challenges. The initial costs are still high, though they're dropping rapidly as production scales up. The technology works best in certain humidity ranges, so it's not equally effective everywhere. Energy requirements for some systems can be significant, though passive systems are becoming more common. There's also the question of water quality and safety. While atmospheric water harvesting can produce incredibly pure water, proper filtration and sterilization systems are still necessary to ensure it's safe for drinking. Regulations and standards need to be developed to govern this new water source. But here's what's really exciting about the future of this technology. Research teams around the world are working on next-generation materials that could make atmospheric water harvesting even more efficient. Some are exploring bio-inspired designs that could work like artificial leaves, using sunlight to power the water collection process. Others are developing smart materials that could automatically adjust their properties based on environmental conditions. The economic implications are staggering. The global water market is worth hundreds of billions of dollars annually. Atmospheric water harvesting could create entirely new industries while solving one of humanity's most pressing challenges. We're potentially looking at a technology that could be as transformative as the internet or renewable energy. This Nobel Prize recognition isn't just about honoring brilliant scientists. It's a signal that atmospheric water harvesting has moved from experimental curiosity to world-changing reality. The materials that can pull water from thin air aren't just laboratory novelties anymore. They're the foundation of a technology that could reshape how we think about water security, environmental sustainability, and human survival in an increasingly challenging world. The future where clean drinking water is available anywhere on Earth isn't science fiction. Thanks to these Nobel Prize-winning materials, that future is already beginning right now.